clustering.
Okay, yeah, so thanks for inviting me. This talk is strong coresets for K-median and subspace clustering good by dimension. So we're going to look at the size of coresets, which are succinct data structures for the K-median and K-means clustering problems. And we'll get new bounds on these. So this is joint work with Christian Zoller. So we know the clustering problem. The general goal is you have a set of points, and you would like to partition your input set into groups such that items in the same group are similar and items in different groups are dissimilar. So in this example, maybe your notion of similarity is what shape these objects are. And here could be one clustering. But if you care about colors, then maybe you would have a different clustering, for example. So it is important to define your notion of similarity, and we'll look at several different notions in this talk. So some examples of relevant distance and similarity measures include the Euclidean distance. So when you group points to try to minimize some of Euclidean distances to their centers, this is called the K-median problem, which we're going to focus on a lot in this talk. When you group points to try to minimize their squared Euclidean distances to the centers, this is called the K-means problem. But you can imagine many other notions of similarity. For example, maybe you just have some underlying metric, and you want to cluster with respect to that distance. Or maybe you have points on a sphere. You care about cosine similarity. Maybe you have sets, and you care about Jacquard coefficient, distributions, KL distance, etc. So there are many notions. Let me just first look at the Euclidean distance, which gives us the K-median problem. So formally, we're given a set P of points in R to the D. We're going to have n points. And we have a number K of clusters. And we'd like to output a set C of K centers in R to the D, which minimizes this objective function. So the cost of P comma C is just the sum over the n points of the distance of the point to its nearest center. Okay, so you're trying to find this best set of K centers C. The set C of centers does not need to be a subset of your input points. Okay, so this is just an arbitrary set of K points in R to the D. Okay, right, so here might be the clustering. And there's no, if I tell you which points are inside of a cluster, in the K-median problem, there's no nice closed form solution for the center for that cluster, which is unlike the K-means problem, this other distance measure. The only thing that changes here is I'm minimizing I'm still summing over all points, but I'm summing up the square distances to the nearest centers. Okay, and here if I tell you if I tell you the cluster, then the center for that cluster is just the average of the points. Okay, so it has a nice algebraic interpretation, and K-median does not, and this causes a lot of problems, as we'll see later in the talk. Okay, so I want to motivate clustering in the context of very large data sets. So we have a very large input set which does not fit into main memory. And because of this, you design different models for coping with it. One is a distributed model. One is a streaming model. I'll go over both of these. So throughout the talk, we're going to think of K as being a moderate number. So think of K as being small. Polynomial in K is OK. But the dimension D of your data points is very large, and also your number n of points is very large. Okay. Okay. So this motivates the notion of a coreset. What you'd like to do is you have your input set P, and you'd like to compress it to a small weighted set S. I'll describe what the weights mean, such that S approximates P with respect to the problem of interest. Okay, so there are many different notions of coresets around. I'm going to use the original definition introduced by Har-Peled and Mazumdar, which is the following. A weighted set S is an epsilon k coreset for a set of points P with respect to the K-median problem, or analogously the K-means problem, if we have this for all guarantee. Okay, so what it says is for all set C of K points in R to the D, we have that the cost, remember the cost is just, in the case of the K-median, would be cost of P comma C would be the sum over the n points of their distance to the nearest center in C. The cost of S comma C is within a 1 plus or minus epsilon factor of the cost of P comma C. Okay, now there are a few things to clarify here. So cost of P comma C, we already saw what that was. Cost of S comma C, so S is a weighted subset of, is a weighted set of points. So what that means is, for each point in S, I compute if I'm looking at K-median, I compute the distance to its nearest center. And then I scale it by its corresponding weight. Okay, and I add up all of those values. That's clear? Okay. And similarly for K-means, I just replace distances with square distances. Okay, so I'd like S to be a small set of points, but I have weights attached to them. And importantly, again, that this holds for all sets C of K centers. One nice property about that is, I can do optimization on the set S. I can throw away the original point set P, just optimize over the set S to find the best set of centers, C. And since this holds for all sets, I can introduce constraints, whatever. I mean, everything is preserved by this set S. Any questions? Okay. Good. So what are some properties that you might want out of corsets? So one is that the union of corsets for sets P and Q. So if I have a corset for P and a corset for Q, I'd like the union of these corsets to be a corset for the union of the points P and Q. And we'll see why in these large data models this is a useful property. So here's the first model, which is distributed algorithms. So if I have a lot of points and they don't fit locally on a given machine, one way of processing them is to partition them across multiple machines. Okay? And one way of using corsets is just to have each machine locally compute a corset of its input points and send the corset to the central server. Okay, so the size of the corset is the communication from this server to the central server, so it's important to minimize this size. Okay, and so this central server will get a bunch of corsets, one for each of the servers. One thing it can do is compute a corset of the corsets if it wants to make it even smaller. Okay, so it could just take the corsets from each of the servers, stack them, concatenate them together. That will be a corset for the union of all the points. But one thing you can do with corsets is compute a corset of the corsets, and that would at least make the local computation here better. Is that clear? Yeah. Okay. Cool. Another application is to streaming algorithms. So one way of using corsets in a streaming algorithm is I'm going to see my n points one at a time in a stream. After I see some number of points, there are too many points to be able to store in my memory, so I compute a corset of those points. Then I see a next batch of points, and I compute a corset of those. And then now I can merge the corsets. I can, by this composability property, I can compute a corset of the corsets, and so on, right? So I can just compute corsets of what I've seen so far. And the nice thing about this approach, which is called the merge and reduce framework, is that my memory is just the size of a corset times the depth of the tree. Okay, so I maintain at most one corset per level of the tree.
You lose an epsilon every time?
Yeah, so good question. So what happens to the epsilon factor? So here I'll get 1 plus or minus epsilon approximation, here 1 plus or minus epsilon approximation, and here when I compute the corset, I'm going to get a 1 plus or minus epsilon approximation of these, so it'll be a 1 plus or minus 2 epsilon. And the next level will be 1 plus or minus 3 epsilon, etc. So I do have to replace my epsilon with epsilon divided by the depth of the tree. And another thing is that if these are randomized constructions, I also have to union bound over some failure problem. I mean, some failure event. Any other questions about this? Okay, cool. Okay, so yeah, so we see that the memory is of the streaming algorithm is related to the size of the Corset, which is important to optimize. Let's see the history of the sizes of Coresets for the K-median problem. So in the original paper I mentioned, the first Corset size was k times log n over epsilon to the d. Okay, so this depends on both n and d, which could be large. In fact, it depends exponentially on d, which was okay for their applications because they were looking at some computational geometry applications.
This is the size of the,
this is the number of points in your set S. Yeah.
And these are all
that you can find.
computable?
What's that?
These are all efficiently computable?
If you consider this time efficient, yeah.
So
yeah.
that's also the time, okay, whatever is the size is also the time.
In these, yeah, I believe so. Yeah, yeah. Okay, so yeah, so this is quite large.
It's probably easy to give examples of metrics where there is no Corset other than the size. It has to be n. You have to take the entire.
Oh, some metrics, yeah.
Yeah.
So here I'm looking at Euclidean distance K-median. Yeah,
In
yeah.
general, we shouldn't even expect such a thing to exist.
That's true. Yeah, yeah, yeah.
What's the computational complexity of just ignoring by any technique what's believed to be the hardness of K-median?
Oh, what is the best sort of parameterized upper bound of K-median in terms of K and epsilon? I think, yeah, I'm not actually, does someone know? I'm not actually sure. Like, so there is some ETH hardness. I don't know what the state is, but yeah. I mean, it's hard to approximate. I mean, so I think Moses Charikar has a paper on this. I don't know the best bounds, but yeah. Yeah. Okay. So this original Corset size, natural question is, does it have to depend on n? And what Harpalet and Kushal showed later is that no, it doesn't have to depend on the number of points. Okay, but it's still exponential in the dimension. What Chen later showed is that you can get a linear dependence in D, but now the log n was back in the complexity. And Langberg and Schulman show that actually you can get a polynomial in KD and epsilon dependence on the number of points in the Corset. And the state of the art before this work, due to Feldman and Langberg, and see also alternative proofs of Braverman, Feldman, and Lang, is KD over epsilon squared. Okay, so n is gone, it's a linear dependence in D.
Is the existence result easy to show? Just what,
No, so yeah. In fact, I'm going to actually focus on an existential result. Yeah. Okay, so natural question here is, well, does the D even need to be here?
So
yeah.
it might be possible that this K-median, you might solve it using more medians than you allow.
Yeah, so they're also like.
But then it might be the case that this is faster than computing the Corset, in which case you would not need to compute the Corset. I don't know the right answer. I'm saying, is this the case or it's not the case?
It's not the case. Yeah, I mean, as far as we know, it could be that, but like sort of a completely different notion of Corset, maybe that allows for some bi-criteria. Yeah, so definitely you can, if K is not a hard constraint, for example, if you allow K prime medians for K prime a bit larger than K, I think poly K log n, then the problem does become easier. But if you have a hard constraint on K medians, I don't know of a better way of doing this. Yeah. Okay. Yeah.
So you're focusing on removing log n terms also, but in this application, like a streaming, you say that log n will. Yeah.
So back for streaming, the log n does come back. Yeah. So we don't. That's an open question if we can get rid of that there. Yeah.
Okay.
So yeah. So our question really is, does the D need to be there? This is the motivation of this work. And the main result we show is that it doesn't need to be there at all. So there is a Corset achieving this for all guarantee for the K-median problem with a number of points that is independent of both n and d. The Corset size is polynomial in k over epsilon. Okay, so it's roughly k squared over epsilon to the fourth. We achieve this in two steps. First, we give a new dimensionality reduction technique for K-median, which reduces the dimensionality of your input points from D to order k over epsilon squared. Okay, so this is the main new thing. Once you have this, that the points live in this lower dimensional subspace, you can actually apply existing corsets for K-median, which, as we saw, are linear in the dimension. So this is in particular why we're getting, if you saw on the previous slide, kd over epsilon squared was the best previous bound. Replacing d with k over epsilon squared gives you roughly what I claimed of k squared over epsilon to the fourth. Okay, so the main point here is this dimensionality reduction procedure.
So what is your randomness model? You're allowed to use randomness, and the points are the input is oblivious.
It's existence.
Yeah, so I will give an algorithm. In terms of randomness, I mean, it's worst case input point set, and you get to use randomness in your construction of the coreset. And but after doing that, it should hold. You should have this data structure which works for any query center. I mean, any set of k points. So there's
the
no.
result is just that it wasn't known that this exists even. That
That's right.
This
Yeah.
is a subset of Euclidean space. Forget about any finding it.
But there's no like randomness in the sense of a for each guarantee. Is that the question, or like it does hold for all possible queries of k centers. I mean, there's randomness in the beginning, but afterwards it's a for all guarantee. Okay.
So what's the best lower bound here?
Yeah. So that's a great question. We don't have non-trivial lower bounds. K is a lower bound. I mean, so it's a great question. As far as we know, especially like you can get lower bounds in terms of d, like k times d. But if d is very small, what is the what is the lower bound as a function of k and epsilon for small d? And it is a sensitive question. So like when d is 1, you can actually get a k over epsilon upper bound. So there is, yeah. So the short answer is that's a major open question in this area, like getting lower bounds for corsets.
What about other geometry? What about, let's say, in a tree? I give you just a tree and endpoints in a tree, and you want to do k median or k.
Well, for restricted graphs, what are the best bounds?
Just on a tree.
Just on a tree.
So it seems like.
Oh, I see. I mean, like once it's restricted enough, you can do things like dynamic programming, right? Or
just existence. I don't. Okay.
Well, like on a line. I mean, so in one dimension, k over epsilon is an upper bound. I'm aware of a manuscript that claims it might get k over root epsilon, but I think there's actually there's a k over root epsilon lower bound as well. But I don't know if the upper bound. Yeah, so I don't know. Yeah.
A tree with arbitrary degrees does it depend on the degree sequence? Okay.
I don't know already. Yeah, for a line, I don't know. Yeah. Any other questions? Okay. So the way the rest of the talk is structured is as follows. So this result was known for Kmeans. Okay, and the contribution of our work is to get it for K-median. So it was shown for Kmeans that you can get a coreset of size independent of n and d, so poly k over epsilon, in 2013. We're going to give an alternative proof of that result, more geometric proof, and this will help it to generalize to K-median. But we'll still need some new ideas on top of that alternative proof as well.
So what was known for K-means?
So for K-means, it was known that you can get this type of coreset guarantee that I described with a poly k over epsilon number of points.
Yeah, but the square root of a Hilbert space is a Hilbert space, so K-median is K-means for a new set point set. It's a Schoenberg. If you take the Euclidean distance to the power of half,
Okay.
this is inside again, it's new points in a different Euclidean distance. So if you solve K-means for the square root of the distances, so you correct, it became K-median. It's a formal, one important formally.
Okay, I'm not. We did look at that.
Space
Yeah.
Metric to the power of half.
Okay.
You're back in Rn. So new point set.
Okay.
Now solve K means for the new point set.
Yeah.
And now all the distances are 1/2. You square back. You get your K.
So there's some issue with that. Okay. So this is these bi-Lipschitz embeddings, right?
No, it's isometric.
But you need to compute new points.
Mhm.
So this already is n. You need to go over everyone. In terms of running time, I don't know about the number.
I'm talking about existence. I'm just, as a theorem in geometry.
Okay, maybe let's get back to see how this is related. Okay. Okay, so yeah, so just we're going to use Pythagorean theorem over and over again. I just want to set some notation. So we have this subspace T, and sort of so we have this point P, we have its projection P prime, we have some other point Q in the subspace, and we have that a squared plus b squared is equal to c squared. And just keep in mind this intuition that if this distance of P to a point Q in the subspace is close to the distance of P to the projection on the subspace, then Q and P prime are close. Okay, this is just saying that, yeah, I mean, it's Pythagorean theorem. So, yeah, actually, getting back to your question,
There are additional points.
Actually, getting back to your question, there is a counterexample for the kind of Corset that we want for K-median. So it actually can't. Something is broken in that argument. I don't know what it is, but
is that,
yeah.
Your points are lying in some sort of on some curve in some higher dimensions, and it's good that your new points are not in the image, not lying on that curve.
Oh, I see. So the dimensionality is.
So you can, if you want, you increase the dimension a little bit, but now they're lying on some curve, and it could that your medians are outside of that curve.
Oh, I see.
Maybe that could be corrected.
Okay, so let me show you a counterexample to that. Maybe it's related. Okay, but okay, here's the main dimensionality reduction procedure, and this is for K-means. I'm just going to talk about K-means first. So let me just describe it existentially first. So let opt be the cost of the optimal K-means clustering. Suppose you somehow know this. The first step of the procedure is to compute the optimal k-dimensional subspace S for minimizing the sum of squares of distances of your points to it. Okay, so this can be done efficiently, right? This is just the singular value decomposition. So this is the best k-dimensional subspace. And note that the cost of using this space S is at most the cost of the optimal means clustering, k-means clustering. Is that clear? Because the k-means necessarily lie on some k-dimensional space, and you're finding a k-dimensional space which minimizes sum of squares of distances. Okay, so you start with S, and what do? You have the following while loop. While you can add k dimensions to S to reduce the cost of the subspace approximation problem by epsilon squared opt, you do it. Okay, so you find k dimensions which reduce the cost by epsilon squared opt if possible. And you just repeat this. Okay? Now, how many times can you repeat this? Yeah, at most 1 over epsilon squared times, right? Okay, so the space S that you get at the end is going to be of dimension at most k over epsilon squared. Okay, each time you're adding k new dimensions. And finally, what is the output of the Corset? You take your endpoints, your points at P, and you project them onto this space S. Okay, so I still have endpoints in R to the D, but they all live inside of this space S. And I also output the scalar delta, which is just the projection cost. Okay, so the sum of squares of distances of the points to my space S. Okay, just a single number.
It's opt.
So opt is the optimal k-means clustering cost. Okay, and now this opt is at least the cost of using the best k-dimensional space S for approximating my points. Because these k-means, they live in some k-dimensional space. I mean, I can take the space spanned by them. And this is the best space. So the cost here of using the space S is at most opt. I start off with the space S, and then this opt here, if I want to make this an efficient algorithm, I can make this opt equal to this cost, the cost, the SVD cost, the cost of the best k-dimensional space S. If I just want to describe an existential algorithm, I can let it be the potentially larger k-means opt. Okay, so yeah, so all I'm doing is adding k-dimensions until I can no longer find k-dimensions which reduce the cost by epsilon squared opt. Okay, clear? Okay. Yeah, sorry. So that answers your question. This is the k-means opt. Let's look at what's going on here. So, okay. So for analysis purposes, let T be the span. Suppose I have a query set C of k-centers. Okay? I let T be the span of those k-centers together with this space S that was output by my dimensionality reduction procedure. Okay, so it's the span of the union of these. Then the first claim is that again, I'm doing k-means right now. The cost of p comma c is equal to the cost of p comma t. So the cost of moving the points to the space t, which I've drawn here the space t as a plane, and t contains the space S, which is the output of this dimensionality reduction procedure. I've drawn that subspace as a line inside of this plane. Okay, so cost of pt is the cost of moving the points to the space t, and p sub t is the projection of the points onto the space, and so I get plus the cost of moving the points inside of the space to the centers. Okay, so is this equality is clear? That's the Pythagorean theorem. Okay? Okay, now I'm trying to approximate this cost, right? I want a Corset, so for any query set C you give me, I want to be able to approximate this. I don't know T, right? I mean, I don't have it anymore, right? So what did I do? I built a Corset. I threw away my original point set P. How am I going to compute the cost of the projection of P onto T if I don't have my point set P anymore? I also don't know the projection of my original points onto T. All I have is the projection of my points onto S. I threw away my original point set. So what I have is what's on the right-hand side here. This is what I have with my Corset. Why? Because if you remember that scalar delta from the dimensionality reduction procedure, that was the cost of moving my points P to the space S. Right? So I have that number. And I also have the projection of my points P onto the space S. Right? That's what I output in my Corset. So I can compute the cost of moving those points to the centers. So I have this right-hand side for my Corset, and I'm trying to approximate this left-hand side, which is the exact answer. Clear? So, questions about that? Okay.
Can I just
Yeah, sure.
It's again, but the original formulation. When you have the centers, how do you get the partition? Or part of the input is both the center and the partition?
So the original input is just the set P, and I'm trying to find the set C of centers, which gives me a good approximation to my
cost PC. I thought it would be dependent on P, C, and the partition associated to each element in C.
Oh, C defines a partition, right? So
it's really the nearest points, or?
Yeah. So each point is served by the closest point in C. So each point in my input set P, I assign it to the closest point in C, and that defines a partition.
Usually the way I understand K-means is that you find the partition, and then you take the average within that partition. It could be conceivably that that's not the nearest point.
Yeah, but how do you find that partition, right? So, I mean...
It's a function of the partition, not of the centers. That's what I'm trying to say. Why are you indexing this by the centers?
Well, because what I'm trying to do is I'm trying to get a compression of my original point set so that now I can optimize on that compressed version. Now, I need to find... So,
the definition, not why...
Oh.
So what is cost PC? So
cost PC is... So think of P as a matrix where the rows are your points.
P is a set of points.
P is a set of centers. And the cost PC is the sum over the points of the square distance of the point to its nearest center.
So you really want the nearest, okay.
Yeah.
And in all of these, the variance, if instead of distance to a single point, you just take the average or the sum of the distances within a cluster, all pairs, rather than adding new points.
So once I can look at all the points that are served by one particular point in C, right? That point in C is the closest point among the centers to some subset of my input points P. And now I can ask, so all of these are going to be in the same cluster. And now a better center might be to take the average of those points, right? I mean, once I fix my partitioning, then the average is
Okay.
Yeah.
What I was suggesting before works perfectly well if the cost of you have a partition of your point set,
right?
And then you look at the sum of all the distances within that cluster, rather than a distance to some new phantom point that you added.
Oh, okay.
That works perfectly well for that.
If you have a partition already,
it should. To me, it feels natural to parameterize this by partitions, not by the centers. But
Oh, I see. Okay, so it's just a matter of parameterizing how.
It's not the same thing.
Yeah, well, I mean, the thing is, like, as I range over query center C, I'm not going to realize all partitions, right? This thing has, like, some VC dimension, and I'm only going to get certain partitions of my input points. So
In the case of the square distance summing over all partitions and summing over, a partition is uniquely, associated to it, there's a number, which is the average of the points in it.
Yeah, but you would never realize particular partitions with Kmeans, right? I mean, there's some ways of partitioning the points for which it just wouldn't make sense to have that partition.
You can minimize them, you're not going to take it, of course. We're used to this.
Okay, yeah. Okay, so this is just one parameterization then. I mean, I want to find the set of centers. Yeah. Okay. Yeah, so just to sort of like crystallize what I just said, like we're going to split the Kmeans cost into two parts. One is the cost of projecting the points onto a subspace T, and the other is the cost of moving the points, the projected points inside of the subspace to the centers. Okay, so T contains the set of centers C. It's just here for analysis, right? Sort of the intuition here is we want our subspace S that we output by this dimensionality reduction procedure to be good for all T. Okay, so I'll describe more what this means on the next slide. But in particular, we want this T. It's going to be important that this space T contains the space S, which is the output of dimensionality reduction, and also it contains the set of centers. So let me just go back to this approximation. Okay. So the first claim is that the cost of P comma T is about the same as the cost of P comma S. Why is that?
Well, that's the termination condition.
That's the termination condition of the algorithm, right? We know that like T, the way it's formed is I'm just adjoining the span of K centers, and so T can improve the cost of S by at most epsilon squared opt. Right? Okay, good. Okay. The other thing that you can show, I'm not going to show it for K-means because I want to focus on K-median, but you can show that this cost, the cost of moving the points, the projected points onto T to their centers, is about the same as the cost of moving the projected points onto S to the centers. Okay? Why is this? Well, since S is contained inside of T, the square distance of a point P to S is the sum of square distances of the point P to the projection onto T plus the square distance of that projection to S. That's the Pythagorean theorem. So I have cost of P comma S is cost of P comma T plus cost of moving the point PT to PS. And just rearranging this, what this means is that the sort of average square distance between projected points onto T and projected points onto S is the cost of PS minus cost of PT. I just rearrange this. And that's at most epsilon squared opt, right? As you already told me, right? This is the termination condition. So what this means is that actually the projected points onto T are sort of close to the projected points onto S on average. And this is for any T. Okay, I found one specific S. And you can show if that condition happens, namely quantitatively if that cost is at most epsilon squared opt, then you can actually show the cost of moving these projected points to the set of centers C is about the same as the cost of moving the projected points onto T to the set of centers C. You can show that that's at most epsilon opt. And this just uses Pythagorean theorem. I mean, this is a very elementary proof of this. Okay. Let me skip that, and I'll give more of the proof for K-median. But you see the overall structure here, so that this term is about the same as this term, and similarly for the other two terms. Okay. So what we've done is we've reproven a result of Feldman, Schmidt, and Zoller, which says the following. Let A be a matrix storing n points from R to the D as its rows. And as we said, in the case of K-means, you can find this subspace S from dimensionality reduction efficiently. It's just the SVD. So let A sub m be its best m rank approximation for some m which is order k over epsilon squared. Okay, remember this dimensionality reduction procedure starts off with the best rank k space, and then it tries to find k directions which improve the cost. the best k would be the next k largest, next k singular vectors corresponding to the next k largest singular values, and so on. Okay, so you'll end up with a space which is at most k over epsilon squared dimensional. And what is this sum of squares of costs to the subspace? Is just the best rank m approximation cost of your original input matrix A. Okay, and what you have is the following property, that if you have any query set C, then the projected points, your original matrix A, its projection onto this space is just the best rank m approximation A sub m. So what they showed is that the cost of moving those projected points to the query center C plus this fixed scalar gives me a 1 plus epsilon approximation. And so that's exactly what we showed. Okay, this is the cost of moving to the subspace, and this is the cost within the subspace. Okay, any questions about Kmeans? Okay, cool. So let's move on to K-median. So this intuition is still true, that again, that if I have a point P and its distance to a subspace is about the same as its distance to a point in the subspace, then that point had better be close to the projection of the point on the subspace. That same intuition is true, but you can't easily split the cost into the cost of the projection plus the cost within the subspace. Okay, because you don't have Pythagorean theorem anymore. And in fact, there's a simple counterexample as follows. You cannot hope for a K-means type guarantee of the following form, where what did we have for K-means? We found a low-dimensional space S. We projected all of our points onto it. And we said that our overall cost is the cost of moving those projected points to the query centers plus this fixed scalar. Okay? That's the type of guarantee we had for K-means. Already for one median, there's no hope of getting a 1 plus epsilon approximation of this form. And here's an example. Okay, so I've drawn it here on the board. So our point set P is going to be n random points on the unit ball in d dimensions. Okay?
Euclidean ball?
Euclidean ball centered at the origin, yeah. Okay. Now, suppose you fix some m-dimensional space S, and think of this m as being very small. Suppose it doesn't depend on d or n. Okay, so I'm fixing some m-dimensional space S. What are going to be the norms of the projections of the points onto this space S? Right, so I imagine taking all these input points and projecting them onto this space S. Yeah, so like if suppose I fix the space in advance to start with, and I take a point and I project it onto this space. Its norm is going to be extremely tiny, right? So it's going to be close to 0. Right? It's going to be roughly like m over d, the squared norm, and I'm thinking of m as being very small, like not depending on d, for example. Okay, so it's going to be the case that almost all of these points have very tiny norm when they get projected onto this space. Okay, and that holds with super high probability. In fact, the probability is so high that I can actually union bound over all m-dimensional spaces. Okay, there are some m-dimensional spaces which go through some of these points, but the claim is that for every m-dimensional space, almost all of the points have norm close to 0 when I project onto them. Okay? Okay. So yeah, so just saying what I said on the board, if this dimension d is much larger than the dimension m of the space, then the projected points will all have tiny norm. And okay, so what if my query center, I'm looking at one median, what if I just query what is the cost of the origin? Now what is the cost of the origin in the one median problem? Well, it's n, right? I have n points on the unit ball. So the cost is n. But if I try to have a coreset of this form, if I plug in the origin here, then this cost is going to be very close to 0. Right? All these points have really tiny norm. Moving them to the origin, this is going to be something very small. But I need a cost of n, so this means that this scalar delta needs to be about n. Right? Otherwise, there's no way I'm going to get a 1 plus epsilon approximation. It's clear? Okay. On the other hand, what happens if my query center is instead a point on the ball. So suppose it's, it doesn't matter which point, but suppose I choose this point, 1, 0, 0, 0. What is the cost of using this point, the 1 median cost? Right, so at some point on the ball, what is the sum of distances of all my random points to it? Right, so if I take if I take a fixed point and a random point on the ball, their distance is about square root 2. And I have n of these points. So the cost is going to be square root 2 times n. Is that clear? Okay, well, if the cost is square root 2 times n, what is this cost? The cost of the projected points onto S, moving them to this point on the ball. Right, all these points have very tiny norm. They're close to 0. Moving them to this point on the ball, this cost is going to be about n. Is that clear? And this delta, we already argued, has to be about n in case my query center is the origin. So this is close to 2n, but it needs to be close to root 2n if I want to get a 1 plus epsilon approximation.
So is the goal logarithmic?
What's that?
So if I just wrote square root of cos squared plus delta squared, is the goal to sketch something or just to algorithmically compute it?
I mean, the goal is to find a Corset for achieving this for all guarantee. And what I'm just saying is that we can't hope for Coresets that have this form.
But what's the guarantee? That I can compute? Or
Yeah, the guarantee is that
I can compute given using this formula.
That's yeah. So the goal is that you can compute, but you want to be able to compute for all query centers. It's not just solving the K-median problem. You want to be able to respond to a query, and this is useful because I might add constraints. Right? I'm not just solving the original K-median problem. I want to preserve the cost for any set of centers. And I'm just saying that this particular form of a Corset will not work.
But if you wrote square root cos squared plus delta squared?
Exactly.
Oh, for this particular point set.
The example, that's kind of.
Did you mean like the square root of like the sum of? Yeah. I mean, so that could fix this particular example, but there's no reason that should work in general, right? I mean, you're saying like take the square root of the sum of distances.
Square.
Yeah.
Maybe you should say where does this example fail if you have squared the distances?
Oh, if you have square distances.
The same computation. Then what
this cost here should be 2n, right?
So that's so the point is that so it's something like Marcus said. There's some normalization issue in the definition of the cost function.
Or if you have 3 types of points.
It is, yeah. I mean, it's kind of a normalization issue, but it's not. Okay, I'll describe the fix that we have to this, and maybe this is what you're suggesting. But okay. So what we're going to do to this normalization, this issue, is we're going to add a special dimension to the projected points that is equal to the distance to the subspace S. Okay? So we're actually going to run this dimensionality reduction procedure. Okay? We get our n points in RD. They all live in this space S. We're then going to increase the dimensionality of the points by 1. Okay? So we're going to make them d plus 1 dimensional. On this extra dimension, we're going to encode the distance of the point to the subspace. Okay? So let me say it, and yeah, now instead of being k over epsilon squared dimensional, they're k over epsilon squared plus 1 dimensional, potentially, living in RD plus 1. And when we have a query C, we're going to map it to this new d plus 1 dimensional space by setting the extra dimension of each point in C to be 0. Okay, so maybe I can just show you the algorithm. So here's dimensionality reduction for K-median. I'll describe it existentially. Let opt be the cost of the optimal K-median clustering. Before it was for K-means. What do? The next step is to compute the optimal K-dimensional space S for minimizing sum of distances. Okay, so not the space that minimizes sum of square distances, the one that minimizes sum of distances. Okay. And similarly to before, while you can add k dimensions to S to reduce the cost of the subspace approximation problem by epsilon squared opt, you do it. Okay, so you just iteratively add k dimensions. You can do that at most k over epsilon squared times as before. Okay, the first 3 steps are the same, except the cost function changed. The last step is the following. For each point P in your point set, you compute its distance to the subspace. Okay? And now what are you going to return? Unlike before, you don't just return the projection of the point onto the subspace. You return the projection, comma, the distance of the point to the subspace.
It's a pointwise fix.
It's a pointwise fix, yeah, yeah. But let's see why it works. Okay. Is it clear how this fix is happening? Like we're adding one extra dimension, which is encoding the distance of the point to the subspace. Okay. So here's the analysis. So again, let T be the space I've drawn here as a plane containing the query center C and the space S, which is the output of dimensionality reduction procedure. Okay, so the first lemma is a close projections lemma. Okay, so I'll prove it this time. Okay, so for k-means we did prove this with Pythagorean theorem. Let me prove it here for k-median. So the claim is that this space T, which contains the space S and C, if I look at the sort of average distances between the projections onto T and the projections onto S, it's at most epsilon times opt. Okay, for any T. Okay, so this is just, I mean, it's elementary. It just fits on the slide. Let me just do it. So the way we argue this is let Q be the subset of points P in your input set for which the distance between the projection onto T, the distance between the projection onto T and the projection onto S is at most epsilon times the distance from P to the space S. Okay? Then, if I just sum over all the points P and Q of the distance between the projection of P onto T and P onto S, then I get at most epsilon opt, right? Because I'm going to be summing up this over all points in P. S was a space for which the cost was at most opt, so I get epsilon opt. Clear? Okay. So otherwise, I'm going to be looking at points for which this distance is a little bit large. So we do have this Pythagorean theorem that the distance between the projection onto T and projection onto S is the square root of the square distance between P and the space S minus the square distance between P and the space T. Okay, to the 1/2. And we also know the distance from P to S is at most the distance from P to T. Okay, so then this is just elementary manipulation. So let's look at, this is exactly from the previous line. And let's just write this difference of two squares as the difference of these two quantities times the sum of these two quantities. Okay? And now what we know is that since we're in the case where the distance between the projection onto T and projection onto S is at least epsilon times the distance between P and S, then we know that this, this quantity can't be too small. Right? I mean, because we know that the left-hand side here is large. It's at least epsilon times the distance from P to PS. This thing here is, distance P to T is at most distance P to S. So this is like at most twice the distance of P to the space. This thing cannot be smaller than epsilon squared times the distance from P to the space S, because otherwise, overall, I wouldn't have this property. Is that clear? Like this thing just can't be too small. So it can't be smaller than epsilon squared times the distance of P to the space S, which means that actually, since this thing is at most twice the distance of the point P to the space S, it means overall I can write this quantity as at most, the distance as just this first term squared over epsilon squared to the 1/2, and I get, at the end of the day, I get the the distance from P to S minus the distance from P to T over epsilon. Okay, so all I did was a case analysis and used the Pythagorean theorem. And yeah, so now what do we know if we sum over all P? We know that by definition of the algorithm, T cannot improve this cost by more than epsilon squared opt, right? And so when I sum over all P, the numerator is going to be epsilon squared opt. I divide by epsilon and I get epsilon opt at the end. Okay, so this is just a proof of close projections, okay? Meaning that the points in T are on average, when I project my points onto T, they're on average close to the projections onto S. Okay. A lemma that actually we just used is that I'll call this distance to subspace, which is the cost of moving my points P to S minus the cost of moving my points P to T is at most epsilon squared opt. And that is just following from the definition of the algorithm again, right? Because T cannot improve the cost by more than epsilon squared opt. Okay. And the final ingredient we need is the following. So let P be a point and CP be P's closest center in C. Then I'll call this distance inside subspace lemma, which is saying that if I sum over all points of the distance from the projected point onto T to the center minus the distance of the projected point onto S to the center, I get at most epsilon opt. And this proof is just the triangle inequality. So the distance of the point PS to the center CP is at most the distance from PS to PT plus the distance from PT to CP. And just rearranging things, I get that the sum that I'm trying to bound is at most the cost of moving the points, the projected points in S to the projected points in T. And that lemma that we just showed on the previous slide shows that this is at most epsilon opt. Okay, so there was nothing going on here. I want to bound this. I apply the triangle inequality here, and it becomes this when I sum over all P. Okay, so what we have is like distance to subspace is small, distance inside of subspace is small. And let's just put it all together. So, okay. So here's the actual distance of a point P to its nearest center. Right? It's just by the Pythagorean theorem I have this quantity. And here's what I can compute with my Corset. Okay? So what do? Remember in the Corset I output the point P projected onto S. And I also output this encoding of the distance of that point to the subspace that I found. Now how do I handle a query? If I have some center C, I adjoin 0 in the extra special dimension. So if I just write out this distance, well, it's the square root of the sum of squares. So it's the distance P PS to 0, that's just the number to 0 squared, plus the distance from PS to CP squared, the square root, okay? And now we're in pretty good shape, right? Because if we didn't have these squares and square roots, then what we've already seen is the distance to the subspace is on average, to the subspace T is on average close to the distance to the subspace S. So these two terms are similar on average. This is the distance to subspaces being close. And we've also seen that the distance inside of the subspace, these two things are close on average. Right? So that's really all the intuition here. So like the reason that when I sum up these differences across all points P, that I get something small is just because of these two lemmas that we've proven. The distance of the points P to S is about the same as the distance of the points P to T by the distance to subspace lemma. And the distance inside of the subspace is also small. Okay, so I'm just re-saying that these two things are close and these two things are close on average. Now we actually have squares and square roots. So we can't just say this. This is just the intuition. But it's really almost as simple, so I can just do it on the slide. Here's the actual distance we want to compute for a point P. here's the distance we can compute with our Corset by embedding this extra dimension. We'd like to show the following, that we'd like to take the absolute value of the differences of these distances, right? Okay. So what is that? This distance, I'm just plugging in this distance here and this distance here, okay? Nothing happened. I just plugged in the definition from the previous two lines. What can we do here to get rid of the squares and the square roots? Well, one thing to observe is that this is the Euclidean norm of the vector distance p to pt, distance pt to cp, right? It just has two coordinates. And this is the Euclidean norm of some other vector with two coordinates, right? And I'm taking, a difference of these norms. I have by triangle inequality, this is the at most the Euclidean norm of this other vector, which is this coordinate minus this coordinate, and this coordinate minus this coordinate. Okay, this is just triangle inequality for Euclidean norm. And now what do? I just say that the 2 norm is less than the 1 norm. So I have the 1 norm here. And now that I look at the 1 norm of this quantity, it's exactly what I want. Okay, so it's the distance, it's the difference in distances to the subspace plus the difference in distances inside the subspace. And now I just add up over all the points. And this will be like the cost of ppt minus the cost of pps. And this will be the cost of inside of the subspace. Okay, so that's the whole proof. Yeah, so again, like the details are not important. Really, you're just using those two properties, distance to subspace and distance inside of subspace, and elementary inequalities. Okay, so yeah, so for K-median, the solution was to add this extra special dimension to the projected points to fix this problem for K-means. So we first gave a new algorithm for K-means, a new dimensionality reduction procedure, and then we adapted it by adding this special dimension. Overall, it gives a Corset of size k squared over epsilon to the 4th for K-means. And this dimensionality reduction technique is very general. Like, so we showed it for K-median, but it also works, for example, for subspace approximation. So suppose I want to, my query centers are not k points in R to the d. My query center is a k-dimensional subspace. And I want to know what is the sum of distances to that subspace. I can run the same algorithm on that. Okay? And in fact, I can run the same algorithm on any problem where the centers fit into a low-dimensional subspace. That's all that's being used in this proof. Okay? So, if I want to find j k-dimensional spaces which for each point, this is called projective clustering. For each point, I choose one of those j subspaces, and the one which my projected distance onto that subspace is minimum. Okay, so this is like combining subspace approximation and K-median, right? I have multiple subspaces, and I choose the subspace for which my projection onto it is closest. I can do that as well. So this gives the first Coresets for all these problems that are independent of both n and d. Yeah, and we do have algorithms for these in the paper, but there are nice open questions there. Okay, so for this K-median algorithm, so we can get nearly, you can get a fast running time as a function of n and d, but we still have the algorithm is still exponential in k. So that so there's a 2 to the k inside of the algorithm. So it's like number of non-zero entries of your input. So it's like sort of input sparsity time plus exponential in k. We think that this can be improved by using bicriteria algorithms. So instead of starting off with the best the best k-dimensional space or a good approximation to the best k-dimensional space, if we start off with a space which is, say, poly k dimensions, which is as good as the best k-dimensional space, then maybe you can get an algorithm which doesn't have an exponential in k dependence. But we haven't worked that out. So that's all. So thanks.